All right, probably we'll start and let the other students join soon. Okay, so this week, what we are going to do is we are going to cover week two topics. I have few problems which I will solve, and then using that, you will be able to, you know, solve your assignment problems. So that is the agenda. I had a look at your assignment too. So there was not much of a solving problem solving thing, but only it touches more about the concepts. So we will look into more into the concepts also. So I have three problems here, and I also tried a different mode of presentation today. Let's see how this works, and you can also give your comments. Um Okay, so before we start, Satvi, could you like to ask any questions?
No, sir.
Okay, all right, thank you. Um, uh, so the people who are going to view this in YouTube later after this session ends, you can also probably you can solve with me while you are watching the YouTube video. Okay. Anyway, you can come back next week and you can give your comments. All right, so let me quickly get started with the course. So this so here, even though I have three questions, I am going to do it a bit faster because we already understand that you are spending around 3 to 4 hours per week, probably more, for this course. So I don't want to take another 2 hours of your time. So I will quickly go through the questions, and also that's why this change in mode of presentation also I've changed a bit. Um, uh, and I will open up the forum to you guys. You can ask me any questions after the end of the session. Okay. So in week two, what we covered was we covered each and every component of a gas turbine engine. So we know that gas turbine basic components of gas turbine engines include inlet diffuser, inlet or diffuser, you can call either way, compressor, combustor, turbine, and all. So these are the different components that we have in a basic gas turbine engines. As you go further in week 4, week 5, week 7, you will end up having few more additional components. Okay. Um, so it's just a glance of what is the gas turbine engines and uh, what are the different components. So quickly, let me check my recordings. Okay. So we all know that there is a inlet. So we know that there is an inlet. We have a compressor. That so we have a compressor this region. So you have a big region for compressor, and then you have a small portion which connects the compressor to combustor, and then you have combustor where you see this flames. Okay, so this is where we inject the fuel and then uh, combust it, and will produce high temperature gases, and this high temperature gases get expansion get expanded in the turbine and then uh, to the nozzle. So in between turbine and nozzle, you will have a small portion of tailpipe, if there is. Okay. So these are basically the main components of gas turbines, and we all know how it works also. So let me quickly go forward. So today's agenda is to uh, detailedly discuss about this inlet, because I see there are few questions that you have in your assignments too, and also something related to combustor about calculations of fuel, which is not really fully touched upon in the lectures, uh, which would be a good idea to touch upon here, and then also something related to nozzle that we will look into. Okay, so you can stop me anytime if you want to ask any questions. Let me go forward with it. So when we analyze intake, so there are different flow characteristics that we probably experience. So we, in the sense, as a gas turbine engine, will experience. So one is during the ground run. So when it is in the ground, the intake is going to be, it is going to be shaped something like this. This is your intake. The red color, uh, you know, it's just a cross section of a circular intake. So it will be circular cross section. So I just cut it actually. So this will be your intake, and this blue dotted lines is your airflow. Okay, and when you are in the ground, basically the velocity of the engine, or the engine is not moving. Our engine is moving at a very low speed, you can say, uh, if it is in the runway. If not, if you just switch on the gas turbine engine, it is not moving. So air is what entering the uh, intake. So when it is entering the engine, uh, you can see that this is basically the streamline that we have here. These dotted lines, these are all streamlines. This is the route at which air enters, basically. Okay, these dotted blue lines. Mm, One second, for some reason it is not showing here. Okay, I think it is. Okay, I think it is taking a little time. All right. So this blue dotted regions is going to be the stream, or you can consider it as a stream tube. This is what is entering the engine. So for a ground run, it would be something like this. So if you go for a climb, which means during a takeoff, during climbing, uh, the flight speed would be little, it's lesser than the velocity of air which is entering the engine. So that's why you see a bigger area of intake. So this area of intake, we can also call this as A infinity. Okay, so this A infinity, actually here, it is greater than A. Let's call this intake. IN. So A in. Okay, this in A infinity will be greater than A in. So it is going to be greater than for both ground run and the climb. Okay, and if you go forward, and if you see a high speed cruise, for example, usually your usually your flight will fly at Mach zero point 0.8 or zero point 0.9. That is basically the sweet spot for minimum TSFC that you will soon realize when you go to turbofan engines and so. So during that uh, you know phase, the during this cruise condition, so your A infinity will be almost equal to A in, a little bit less. Okay, so this stream tube keeps on shrinking at the on the other side. Okay, this is how the intake will be. And then for a top speed, this A infinity, which is this area of intake, or the area of the uh, you know what do you call, the flow area, which is actually providing the m dot, this will be less than the area of the intake. So this is how it will be in the top speed. Okay, so you will see an a question in your assignment too, asking where does the diffusion happens. Okay, so at that time I'm not going to give you the answer for that, but you should think a little bit, uh, what is happening, where the, so inlet or diffuser, that is what diffusion is going to, so this inlet until it reaches compressor is the diffuser, right? You can also call this as an inlet, or you can call this as a diffuser. Okay, so where the maximum diffusion is going to happen, or something related to that, the question is. So for which of these conditions, you may need to think a little bit and answer it carefully. Okay, so so these are the different flow characteristics in the inlet of the intake of the gas turbine engines. Okay, and moving forward. So here I have a sample question, like simple derivation that you can do it by yourself. So prove that. So we saw this A infinity, right, in the previous slide. We saw this A infinity. This A infinity uh, is the capture area. It's the air present in within this area is getting into the gas turbine engines. So how is this related to Mach number? So that is the question we have here. So what is this capture area? What is the relation between this capture area and the Mach number of this peak? So we saw that these capture areas keep on decreasing. So what is the relation? So this is actually the relation we have here. A infinity is lambda by m infinity, and lambda is nothing but something like this. So you can prove this by your fundamental equations. So I have the int here. So you have mass flow rate, right? M dot infinity. M dot infinity is rho infinity, A infinity times V infinity. So one second. Okay. So m dot infinity, we all know it's a rho AV, and ideal gas law, we know it's rho equal to P by RT. So, and we also know the Stokesonic speed here. So if you just substitute these things over here in the m dot infinity, and if you rearrange to A infinity, you will get the relation. And you can see that A infinity is actually inversely proportional to m dot infinity, and this is what we literally saw in the previous slide. As we go from m dot m infinity increasing means from ground run to your going to supersonic speeds, right? So during takeoff your m infinity would be less, and at a high cruise missile, it will, sorry, high cruise speed, the m infinity will be higher than the ground or climb, and at supersonic speed m infinity will be maximum. And so as m infinity increases, A infinity decreases. So this you can prove it for yourself. So now we have our first question. The question is, during the ground run, a turbofan engine ingests airflow at 100 kg per second through an inlet area of 1 meter. Okay, so it's a turbofan engine. Maybe currently we don't know what is turbofan engine. We will learn about it, but let's just assume it's a gas turbine engine, and the inlet airflow rate is 100 kg per second, and the inlet area A1, A in is what we saw in the previous slide. Is here it is A1. Okay, A1 is 1 meter cube. If the ambient condition is P infinity and T infinities are given, calculate the area ratio for different free stream Mach number. So basically, we need to apply whatever the relation that we saw in the last slide. So what is the value of Mach number where the capture area is equal to inlet area? That is also we need to find, and also we need to draw air stream tube for various Mach numbers. So this would be interesting. We will see how it is done. So we have a given. So these are the given data that we have. M infinity is given. Area the intake is given, and the free stream conditions are given. And what we need to calculate is we need to calculate A infinity by A1 basically for various Mach numbers, and we need to find out what is the Mach number in which the capture area and the inlet area are same. So that is the second one, and the third one is to draw stream tube. So we are going to use the capture area equation to get this. So you just need to divide it by A1 to get. Okay, for the first we need to find out lambda. So for lambda we have m dot is 100 kg per second, P infinity is 100 kilopascals. R I'm taking it as 287, it's for air, we all know. And then temperature T infinity is 288 Kelvin, and gamma is 1.4. These are the two things I'm assuming. R is 287 joules per kg Kelvin, and gamma is 1.4. These are the things I'm assuming. Okay, and if you do this, the lambda will come out to be around 0.243. This is a simple calculation, that's why I'm not getting. I mean, you can do this calculation by yourself. So 0.243. So if you substitute this all together, you can write this relation. You can just divide it by a1 here and here. Okay, dividing both sides by a1 to get a infinity by a1. So with this, you can get a infinity by a1 to be 0.243 by m infinity. Okay, so the next thing is we need to calculate what is the uh, different for different m infinity, what would be your a infinity by a1 or d. Here I'm also plotting d infinity by d1. So how would it look? So for, let's say this is your intake. Okay, in the right hand side here, this is your intake. So when we go from, let's say for example 0.01, if I want to calculate how much would it be. So what you need to know, you need to do is clear, right? So you need to find out a infinity by a1, which is nothing but 0.243 by m infinity. So you just substitute m infinity to be 0.01. So this will correspond to 0.01, which will be corresponding to 24.3, right? So if I do that, I will have uh, area ratio to be 24.3, and I also found out the diameter ratio, because that will give you a good perspective of how big this is, right? So if your inlet is d1, if your intake is d1, okay, here intake diameter is d1, for Mach number to be 0.01, what would be your diameter is 4.93. So your capture area uh, from which air is going to enter your intake is 4.9 times bigger than the diameter of the intake itself. So that's why at low speed your capture area is very big. Okay, so to give a perspective, I have drawn this as a dotted line here. N infinity is very big. So at low speeds you will have a very high capture area. That is the uh, thrust in this. And then uh, for m infinity equal to 0.05, you can calculate similarly. I am leaving it as an exercise. And for m infinity equal to 0.1, let's say, so for 0.1 you have, so you just need to, instead of here, you just need to substitute 0.243 by 0.1. Okay, this is what you need to do. So you just need to substitute the m infinity that you have to get a infinity by a1, which is coming out to be 2.43. Okay, and if you corresponding, so how did I convert a infinity to a infinity by a1 to d infinity by d1? That should be straightforward, right? So a infinity by a1 is nothing but, so if you assume it as a circular intake, which is mostly the case, so you can write this as pi by 4 d infinity square divided by pi by 4 d1 square. So pi by 4 cancels, so it's d infinity square by d1 square. So if you want to get d infinity square by d1, if d infinity by d1, you just take the square root of whatever you get at a infinity by a1. Okay, so now if you do that and if you try to plot it, you can say, yeah, if you try to plot it for m infinity equal to 1, you can see the capture area has reduced compared to 0.01, if you remember. Okay, and let's say I will go forward with the increase in m infinity to 0.8. So if I go to 0.8, the a infinity by a1 comes out to be 0.3038. Okay, and you can see that for cruise speed, your d infinity by d1, which means the capture area is less than your or you can say it's half of your d1. So let me also plot this. Yeah, so this red dotted line here corresponds to the capture area. So only the air which is within this area enters your engine. Okay, so that is the whole idea of this capture area. So to give a perspective, I plotted all these three. The blue dotted line is for 0.01, the green dotted line is for 0.1, and the red dotted line is for 0.8. So as you increase the Mach number, your capture area decreases. That's the takeaway of this exercise. And the final thing we need to calculate is for what uh, Mach number or for what flight speed, the capture area and the intake diameter will remain same, right? For that, what would you do? You just need to make a for that a infinity by a1 should be 1. So uh, if you just rearrange the same equation, you can get m infinity to be 0.243. So that's the so if you fly it, let's say 0.243 as your mark, if you fly at 0.243 mark, the capture area and your inlet diameter will remain same. So this is a crude. That's the idea that I want to give in terms of intake. So do you guys have any doubts in this? Or should I proceed with the next question? Maybe let me wait for 1 or 2 minutes. So it's the concept is same. As a infinity increases, you have your m infinity. M infinity increases, a infinity reduces. That's the thing. Okay. So this is about intake. The second is about your combustion chamber. So you might have you know in the combustion chamber, what we usually worry about is the turbine exit temperature or the exit temperature of the combustion chamber or turbine inlet temperature. Both are going to be almost same. Uh, or the fuel uh, you know fuel ratio that we add it, or the amount of fuel that we add in the combustion. But what really happens in the combustion chamber is you have air and you are adding fuel, and these two has to mix and then burn. And when it burns, the temperature that you reach is a function of different parameters. For our case, it also depends on what is the ratio of this fuel to air. Okay. And also what is the expected products that comes out. So that also is going to determine the exit temperature of the combustion chamber. uh, so using this only, you will control the exit temperature of the combustion chamber. The reason is, the once the air exits the combustion chamber, it's entering the turbine, and the turbine, we have material limitation. We cannot exit certain temperature, right? uh, Either we need to cool the turbine. Even if you cool the turbine to a maximum extent possible, maybe you can reach up to 2000 2200 Kelvin. That's the current state of technology, probably a little higher. So but with combustion, maybe you can even generate 4000 kelvins or 3500 kelvins, but that is not what we want. We have to limit our temperature to a lower value. So what happens in the combustion chamber is a entirely different, it itself is an entirely different subject. If you are interested, you can take combustion courses and you can learn more about it. But here what we are going to do is we are going to do a simple calculation. What would be the air fuel ratio of this thing burning inside the combustion chamber? Okay. So usually any fuel, aircraft fuel, aviation fuels are a hydrocarbon. Basically it will be mostly kerosene. Sometimes people go with different variants of hydrocarbon. So here there is an hydrocarbon. We don't know what is that hydrocarbon, but they are given a composition of 85% by mass of carbon and 15% by mass of hydrogen. Okay? But they are given the total molecular weight of this fuel. Now, what we should determine is, we should determine the number of moles of air required for stoichiometric combustion. We will see what is stoichiometric combustion. But if my air and fuel mixture undergoes a stoichiometric combustion, what would be the number of moles of air that I need to undergo this stoichiometric combustion, and what would be the number of moles that I would be producing per mole of fuel, is what they are asking. Okay, so let's say if I burn a mole of fuel, what are the different products I will get? What is the number of moles of those product I will get, is what they are asking. Also, they were asking us to calculate the air to fuel ratio, which we will get. Okay, so for this stoichiometric combustion, which does not really happen in any of the combustor in real engines. Okay, but just to give you an idea, so the given is here, molecular weight of the fuel, carbon, what is the mass fraction of carbon, and mass fraction of hydrogen. These two are given. So And then we need to calculate the, as I said, number of moles of air and products, and air to fuel ratio that we need to calculate. And so how would we calculate this? Any idea? So would you?
No, sir.
Okay, so usually, so it is basically coming from the molecular weight of the fuel. So the molecular weight of the fuel, how do we calculate? So okay, it's a hydrocarbon fuel. So what does it hydrocarbon means? There will be carbon and hydrogen, and there will be some X or Y. So this X and Y is what we need to calculate, right? So this X and this Y is what we need to calculate. Or ideally the hydrocarbon is CXH1. Okay. Now, so if I want to calculate the molecular weight of the fuel, how would I go forward with this? You know how many carbon atoms are present. So it's X carbon atoms multiplied by molecular weight of carbon, so which is 12, plus Y hydrogen atoms plus molecular weight of molecular weight of hydrogen, which is 1. So basically the molecular weight of fuel you can calculate as 12x plus Y. This is how you will calculate. Now what they said is YC, which means 85% of the fuel is by mass, it's carbon, which means how would I put? So 0.85 times the weight of the fuel here, which is molecular weight, is nothing but this 12 times X. That is what they are telling. And remaining 0.5% of the fuel is nothing but this Y. Okay. So this is the you know definition of this mass fraction of carbon and hydrogen present in a fuel. Now, with these two informations, we need to come up with uh, we need to find the X and Y. That is our first goal. So what we can do, we have these two. Maybe we can divide these two things. We can divide these two, which becomes 0.85 by 0.15, which will be equal to 12x by y. Right. So now you have one equation over here and another equation over here. Okay, 12x by y equal to 0.85 by 50, and you have 12x plus y to be molecular weight of the fuel, which is nothing but 114.15. Okay, so with these two equations you have two unknowns x and y. You can substitute the second equation in the first equation and you can find. So how would I do it? So maybe you can write 12x to be 85 by 15y. Okay, and then you substitute it here, which would be 85 by 15y plus y equal to 114.15. So this will give you y. Y is nothing but 114.15 divided by 1 plus 85 by 50. So this will be your y. Once you find y, you substitute in either of this equation, you get the x. Okay, is that clear? So if you do that, what would happen? Let's say if I want to find y, how much would that y be? So 1 plus 85 by 15, 114.15 divided by this. So y is coming out to be something like 17.1225. Okay, and then let's say we substitute it in the first equation. That becomes x is equal to 114.15 minus 17.1225 divided by 12, which would be, how much would this be? Something, it comes around 8.0856, something like this. Okay, so which means the fuel is nothing but C8.0856 H17.1225. But we all know the fuel cannot be like C8.08, it has to be some integer, right? So probably there might be some problem in finding the molecular weight of the fuel. So this molecular weight of the fuel, they find it using different techniques, measurement techniques. When they do it, they get some molecular weight. From there, they know that its carbon is 85%. Carbon and hydrogen is going to be there. What would be the percentage of this carbon and hydrogen which will contribute to the molecular weight of this? Something like that they will do. So, but the closest fuel this you can find is it's going to be C8H7. Okay. So if you assume that this is closely equal to 8 and this is closely equal to 17, it's going to be C8H17. So this is the fuel that you have. Okay, is that clear how I did this fuel? What is the fuel? So if it is given in terms of biomass, you can now convert that into fuel. What is the amount of carbon and hydrogen, moles of carbon and hydrogen present in the fuel? You can find. Okay. So now that we know the fuel is C8H17, let's go forward and find what is stoichiometry. So first of all, the question is, what is stoichiometric combustion? So stoichiometric combustion is something that we would like to happen, and we would expect ideal set of products. For example, if you combust hydrocarbon, the combustion is nothing but oxidation reaction. If you combust a hydrocarbon, what you would expect to happen is, in the presence of air, you want this carbon to convert completely into carbon dioxide. You want this hydrogen atoms to get completely converted into hydrogen, water, basically steam in this case. So we want the hydrocarbon to convert from CO2, convert from C8H17 to CO2 and H2O. And since air has nitrogen, we don't want nitrogen to react. We want that to be separate. So it's like ideal set of products that we like to have. And if we want to have this set of products, uh, uh, what would be the amount of air I should supply? Because air is going to provide you the oxygen. So if I want to oxidize this 8 moles of carbon and 17 moles of hydrogen, how much air should I provide? Is what uh, you know question is asking. So if I want to write this in terms of equation, which we already studied, uh, it's going to be C8H17 plus A times O2 plus 3.76 N2. The reason why I wrote like this is air. Okay, so the air has around 79% of nitrogen and 21% of oxygen. Okay, so if you do some calculations, if you convert this to moles, okay, so let's say if you assume that 1 mole of oxygen, for 1 mole of oxygen, if you do 79 by 21, you will end up having 3.76. Okay, so if I have 1 mole of oxygen, with it I will have 3.76 moles of hydrogen. That mixture is what is air. Okay, because we know air contains 79% nitrogen and 21% oxygen. So that is why when we write it in terms of reaction, we write it as O2 plus 3.76 N2. So this together constitutes as an air. And we need to know what is the number of moles of air, which is I am denoting it as A. And then once it combusts, I need to know what is the moles of P, Q, and R I will be getting. Okay, so that is the agenda. So usually if we want to, basically we need to balance this reaction, so that which we already did in our high schools. So we are going to do the same thing. We have 4 atoms, so we have 4 equations. You can do balance of 4 equations, and we have 4 unknowns. You have A, P, Q, and R. Okay, so you have 4 atoms, 4 unknowns, then which means your system is fully defined and you can solve to get A, P, Q, and R. Okay, so What would be those equations? Let's say if I want to write, C would be, you have 8 atoms in C8H17, and you don't have anything on R. So in the left hand side you have only 8. In your right hand side you have 2 times P. Sorry, it's not 2 times P. Still, second, yeah. So you have one carbon dioxide, so it will be just P. So this is the atom balance equation for C. So P is equal to 8, which you can automatically write. And similarly, if I want to do for hydrogen, it would be 17, which will be equal to, we don't have any hydrogen in R. So, and you have on the right hand side, you have 2Q. Okay. So this will give Q to be 17 by 2. Okay. Similarly, you can do for O and N. So for O, how will you do? For R, it will be 2 times A is equal to, we don't have any oxygen in our fuel, so there won't be anything coming on the left hand side other than 2A. And on the right hand side, we have oxygen in both carbon dioxide and water vapor. So you can write this as 2P plus Q. Okay, we know already P and Q. So you can substitute and you can get A out of it. Similarly, if you do for nitrogen, it's going to be 2A into 3.76, which will be equal to, nitrogen is coming out as nitrogen, which will be 2 times R. So you can remove these 2, and then this R can be written as 3.768. Okay, so this is the, so you can also find A similarly. So if you, yeah, if you do this, what you will get is A to be 12.25. Okay, and let's substitute here also 12.25, and R is going to be 3.76 times 12.25, which will be 46.06. Okay. This is the number of, at number of moles of air, carbon dioxide, water vapor, and nitrogen. So this is how you calculate the stoichiometric combustion and the number of moles of air and products that you will have. Okay, so I hope it's clear for you. So what else is remaining? I think air fuel ratio is remaining. Let's go forward. So this is our equation. We just need to find out what is the air fuel ratio. We already know what is air fuel ratio. Air fuel ratio is nothing but mass flow rate of air by mass flow rate of fuel. You can write the you can either write it as mass flow rate, or you can also write it as mass of air by mass of fuel. So here you can remove this dot. Mass of air by mass of fuel. Mass of air is nothing but number of moles of air times molecular weight of air divided by number of moles of fuel by molecular weight of fuel. Okay, so mass of fuel is moles times the molecular weight of fuel. So that's what I just substituted it here, and then I have substituted certain values here. You should be little careful here. So we all know molecular weight of air is something like 28.8, right? But what we also need to know is the number of moles of air that you have here is not just 3.12.25. It is 12.25 plus 1 mole of O2, sorry, multiplied to 1 mole of O2 plus 3.76, right? So there is 1 mole here, there is 3.76 mole here. So total is 4.76 moles. So to 28.8 grams per mole corresponds to 4.76 moles of air. So the total number of moles of air is nothing but 12.25 times 4.76. This you should be a little careful. Okay, this is because it's a mixture. That's why we are doing this. And then so fuel we are considering, we are taking it as 1, and we found everything for 1 mole of fuel only. So, and then molecular weight of fuel is also given, which we are using it. And if we calculate it, it will come out to be 14.87. So this is how you calculate the air fuel ratio. I hope there is no question still now. You can stop me anytime, and we can, if you have any questions, you can stop me. Okay. Now let me move forward and finish the final question that we have here. So this is about nozzle, as I said. First question about inlet, the second is about combustion chamber, and third question is about the nozzle, whether it is choked or not. That's what we need to find in this. Uh, that's what they are asking in this question, basically. So a turbojet engine powers an aircraft flying at an altitude of 11,000 meters. Okay, so it is flying at an altitude of 11,000 meters, which is 11 kilometers, where the ambient temperature and pressure are given to 16.7 Kelvin and pressure is 24.475 kilopascal. The flight Mach number is zero point 0.9. Okay, so that is the Mach 0.9 is the flight speed. The inlet conditions of the nozzle. So the air has gone through compressor, combustion chamber, turbine, and then it is entering nozzle. When it enters the nozzle, the temperatures at the inlet of the nozzle are 1000 Kelvin. So this is supposed to be temperature. For some reason it's missed. So it is 1000 Kelvin and 60 kilopascal. Okay. The specific heat ratio of air and gases at the nozzle are 1.4 and 4 by 3. There are two different specific heat ratios. We will understand why. Okay. The nozzle exit Mach number is 1.27 and the fuel air ratio is negligible. Suggest whether the nozzle is choked or not. That's what. So we have given inlet conditions of the nozzle and also the ambient condition. So if the gases go through the nozzle, will will that condition be choked or not? Is what they are asking. So the given parameters are these parameters which we already discussed: the pressure, ambient pressure and temperature, and also the flight speed. And the exit Mach number is given, and the inlet conditions for the nozzle. Okay, so inlet conditions for the nozzle is, I have written it as a P05, T05 and gamma gas. Okay, so you must have noticed why there are two different specific heat ratios. So what happens is, while we know that air has a specific heat ratio of 1.4, but as it goes through the combustor, it reacts with fuel and it produces, we saw in the previous in problem, that it produces carbon dioxide and nitrogen and water vapor. And what this does is, because of this, the specific heats will be different as it goes to the as it comes out of the combustor. The air won't be just air. Instead, air will have its the combustion products also. That's why we call it as a gas when it comes out of the combustion chamber. And for that, since it has all the other molecules, CO2, H2O, and all other things, the specific heat ratio would be different, and that's why it's given as a separate specific heat ratio, which is 4 by 3. So you should be very careful. So only this gas is going through the nozzle. So when you are doing calculations for the nozzle, the gamma, the specific heat ratio that we use should be for the gases, not the ambient air. Okay, so that's why I've written it here, gamma gas to be 4 by 3. Okay, so and we need to just find whether nozzle is choked or not. And how do we find it? We know that there is some condition called choking condition. Choking condition is nothing but at the throat the Mach number will be 1. So as the gases go through the nozzle, where if at the throat if the Mach number is 1, then we say the nozzle is choked. And the pressure when the Mach number is equal to 1 is what we call it as a critical pressure. It is also, if the nozzle is choked, it is also called as a throat pressure. Okay, so we have this relation here. We know how it came. You can go and revisit week 2 lectures. So this is the choking condition that we have here, and here we use something called gamma H. This gamma H is nothing but this gamma gas. Okay, so we write this as a H. We tend to follow this in our lectures also, because it's a hot gas, and air which enters is a cold. So we use gamma C for that and gamma H for the hot gas to differentiate between these two. And the reason we call this hot gas is it has undergone combustion chamber, and the temperatures are high in the combustion chamber. That's the main reason. Okay, So if you just simply substitute all these things together, you should be able to find out whether the nozzle is choked or not. But when do you say it is a choked is when this critical pressure is actually greater than the ambient pressure, which means the nozzle has expanded till the critical pressure, but the ambient pressure is still less. That is what uh, that is when this choking phenomena will happen. If the ambient pressure is more, the air won't be able to expand till a lower pressure. The air will be able to expand only till the ambient pressure. That is why we write P9 to be equal to P infinity for non-choked condition. But once it chokes, the pressure will not change. That's why we write P9. P9 is nothing but P exit. Okay, basically P9 is P exit. The reason we have this numbering is because in a turbojet engine, we tend to write this as a 9 because of different stations. Okay, P9 is nothing but P exit of the nozzle. So when the nozzle is choked, there is no way it knows that there is a ambient and we need to increase the pressure to ambient pressure. That's why at the exit the pressure P9 is equal to critical pressure. Whereas if it is unchoked, the Mach number will be less than 1, and the unchoked means the critical pressure is lower than the P infinity. So you can actually understand that ambient is somewhere P infinity. So let me adjust my flow to P infinity. So that is what will happen inside a nozzle. Okay, that's why we write exit pressure to be equal to P9 is equal to P infinity for an unchoked condition. And if it is perfectly expanded, which means Pc equal to P infinity, and we will have Mach number equal to 1 at the nozzle. So if it is not choked, Mach number would be less than 1. So please remember that. If it is choked, the Mach number will be equal to 1 at the exit. And here we are, whether we are using, if we use converging nozzle, then we will have Mach number equal to 1 at the exit. If we use converging diverging nozzle, and if the nozzle is choked, we will have supersonic flow later. Okay. Anyway, so to find whether the nozzle is choked or not, we need to just use this condition. So P05 is nothing but the inlet condition. The stagnation, temperatures and pressure is given. So if you substitute them here, P05, yeah, so if you substitute the gamma H, so we don't know the nozzle efficiency, we can take it as 1 here. Because it's not given in the question. If it is not given, you can take it as 1. And if you find this P05 by Pc, if you do this calculation, then what you will have is P05 by Pc is 1.8527. Okay, so we know that P05, what is P05? It is 60 kilopascal, which is entering the nozzle divided by Pc. This is what the P05 by Pc ratio is. So what you can do is you can rearrange this to find Pc. So if you do this, Pc would be equal to 32.385. And what we know about ambient is something like 24.47. So this Pc is actually greater than P infinity. So which means our nozzle is choked. Okay, so if the pressure is greater than P infinity, our nozzle is choked. Okay, the reason, so you might be interested in the reason for this. Why do we say it's a choked and non-choked? So the reason is when Mach number is equal to 1, once Mach number reaches 1, what do you mean by Mach number equal to 1? This is velocity divided by speed of sound. Let's call it C, or let's call it A. Okay, so which means the velocity of the flow same as the speed of sound flow. Okay, so when I'm talking, the rate at the speed at which my voice propagates, or the sound propagates, is actually the speed of sound. So what we are telling is the flow has reached a very high value such that it matches the speed of sound, which means the information usually travels at the speed of sound. So now my flow is also traveling with the same speed, which means my flow will be catching up the information. So if my exit pressure, so for example, if, let's say there is a nozzle, okay, this is the pressure is high here, and then it continuously decreases. Okay, so let's say if I want pressure low here, and velocity increases during the thing. So this is x, this is my nozzle. So what happens, my pressure will be continuously decreasing, and let's say if I plot the velocity, let me plot velocity, velocity would be continuously increasing. Okay, so at this point, let's say, so at this point, let's say I am reaching Mach number equal to 1. So which means the rate at which information is progressing is same as the flow speed. So there is no way that the there is no way the information can go backwards. For example, the flow is happening in this direction. So let me change a different color. The flow is happening in this direction, and I have the ambient pressure is on the exit. Okay, so if the flow here, air here, if it needs to know that my exit is P infinity, it has to travel backwards, right? The information has to travel backwards. But what happened, all this information travels at velocity a. Okay, but what I'm going is I'm going at some velocity. Now this velocity has reached a here. Okay, so because of this, there is the rate at which it is traveling is same as the rate at which I'm moving. So the fluid will never know that there is a P infinity. That's why it will expand till PC. So this will be something like PC. That's why it will expand till PC, and it will stay there. If it is a diverging portion, it continues to increase. Sorry, PC will continue to decrease, velocity will continue to increase. So that's the reason when it is choked, we say that exit pressure is PC, and when it is not choked, we say if it is not choked, what happens? The A will be higher than the flow of velocity. So as the velocity goes, it continuously keeps on getting information that outside my pressure is lower. Sorry, outside my pressure is higher. So what it is, it doesn't expand till here. Instead, it expands only till P infinity. Okay, this is, let's say, for unchoked nozzle. So since it knows that there is a exit is P infinity, let me, so it also expands only till P infinity. That's why we write exit pressure to be equal to P infinity for a unchoked nozzle, and for a choked nozzle, exit pressure is actually same as critical pressure. So that is how we uh, do this calculation. That is how we, this is the theory behind why we select the exit pressure to be same as exit pressure or critical pressure, depending on the condition, there is choked or non-choked. All right, so I hope this is clear. So if you have any questions, you can ask. Satvik, did you understand why it is called choked and unchoked? I hope it's clear.
Yes, sir.
Okay, so if you have any doubts either regarding these three questions, or if you have any doubts regarding the course content, you can ask me.
So I'm not actually having doubt. I'm just learning of these things. So maybe later I can
Yeah,
calculate.
yeah, sure, no problem. You can go through the contents, or you can go through video also, and you can come back to me if you have any doubts. It's all right.
So, sir.
All right, Satvik. So there was another question from last week. I don't know whether you have attended or not. Um, in the last week, there was a question about working of centrifugal compressor. How do we do it? So I was not able to explain properly because I couldn't also draw things properly. So I have this nice picture from the textbook, one of the textbook. Uh, uh, so we usually study axial compressor in this courses. Centrifugal compressor we don't really go through it much, because centrifugal compressors are used in the, in fact, previous, the uh, the engines which have been found, uh, initially by, we call it Vittel engines. So those engines, they are the, so I think he is a British engineer, Vittel, or German maybe. There are two people who separately found the gas turbine, uh, engines. So when they use the, centrifugal compressors rather than actual compressors. So now also it's been used, but its usage is limited. So, but it's been used for other industrial purposes. So in a centrifugal compressor, what happens is you can have a very high pressure ratio within a stage, and how it happens is because of the rotary motion of this impeller. The rotary motion, the impeller is nothing but this thing, the thing we have here, the impeller. It will be connected to the turbine and it will be continuously rotating, and you have this, blades which will be, yeah, these are the blades that we have here. So these blades, what it does is it guides the, uh, it rotates. Because of that, it guides the flow in the actual direction. While doing that, so because of the centrifugal motion of the air, it gets compressed during this motion of the flow from the center to out. Okay, so it might go something like this. And then what you have is, you also have something called diffuser. This part here is diffuser. It is stationary, while this is rotary. It will rotate with some omega. This is stationary diffuser. What happens is, when the flow comes, there will be veins like this, which again, guides, and it also has increasing, area, so which actually increases the pressure again and reduces the velocity. So that is not the only reason that we have the veins. It also guides the flow to a, you know uh, in a proper way, because this is a radially outward flow. It has to guide it and send it out through outlet. So that's why we have this diffuser veins, which guides, and then, to sense the uh, flow outward. So there will be two stages of, pressure rise. Basically, compressor pressure has to rise. There will be different places this pressure rise will happen. One is at the impeller. When it rotates, because of rotary motion of this impeller, it puts a tangential force on the air, radially moving uh, air, and because of that it gets compressed, uh, and then, uh, during it goes when it is going through the radial, the diffuser veins, it again gets diffused and gets more compressed. The diffuser usually increases the pressure. So basically, same thing will happen here. In addition, it also corrects the direction of. So these two things, there will be some percentage of compression happens in the impeller motion. Because of the impeller motion, some amount of compressor happens in the diffuser. So that is how this centrifugal compressor works, basically. So there was someone asking this question: how does this work? There are quite a good amount of videos in YouTube also. There's also one lecture from SK Som. If you, uh, maybe you should, Professor SK Som, from IIT KGP. You can look at this lecture also to know more about this. And also there are good books you can go through. I hope that clears a question of one of the student who from last week. Anyway, with that note, I will stop here. If you have any questions, you can come back again next week, and then we can discuss. Okay. All right.
Okay, sir.
Thanks, Satvik. Thanks for attending. Um, we will meet again in the next week.
Okay, sir. That's it.
Okay, Satvik. Bye bye.